without forcing. That's a problem there.
And thank you for coming. It's pleasant to that. So we have 3 out of 7 today. Maybe there will be a couple of people more. And if someone is not able to come, we'll just share recordings. Hopefully they will work. So there will be. If you have seen slides that I've sent before, they look like ugly, scary, and long. But it's just my lack of talent to explain it in a short, concise way. The subject of today's meeting is white sea. And maybe if we talk and we interact and we listen to each other, it will be more important than the content of the slides. The next lecture on Thursday will be probably the most complicated in the whole course, and there will be important equations, but not today. So
I see there are some a slide, the most important slide here.
Well, how are you?
Good, all right.
Very good. Did you survive the snowfall? Yes.
Yeah. Very good.
And if anyone is interested to submit homework, you can do it by email or in print. So I will overview what we did briefly. And, there will be main message, which is mostly philosophical rather than mathematical. We need to prepare to next lecture, which will contain important equations. So when we will meet on Thursday, you will need to focus what is on slides. Right now, it is auxiliary, the most important what we talk about. I can even try to summarize it in a couple of words and then go over. So some of you may have tried to do homework, and when we were discussing things last time, we have seen that the goal is to predict the properties of materials and molecular dynamics and their response to external perturbations, which needs to sometimes go beyond Newton's equation and focus on quantum properties. And for quantum properties, one has Schroedinger equation, which the answer, the outcome of Schroedinger equation is wave function, which can be time independent, time dependent, but it does depend on positions of electrons, nucleus, and if you have more than one interatomic distance, more than one electron, the arrows that we did in class and you did in homeworks are all arguments of the wave function. And each vector, which we symbolize with letter R with arrow, is 3 components, x, y, and z. So it is a function of 6, 12, 100 variables. This is bad. In our regular life, we never find functions of 100 variables. It's not a good mathematical problem. There are some modern approaches with machine learning and cheminformatics when one tries to find correlations in multi-dimensional space. But for pure mathematical solution, even with powerful computers, this is not well-defined parts. So we need to look again, recognize which mathematical problem we are solving, and try to reduce the number of independent variables. This is not only the goal of today's meeting, it is goal of the whole subject of computational chemistry. If we would have infinite power of computers, then we could stop our lectures last time. Formulate Hamiltonian, formulate molecular Schrödinger equation, and solve it. That's it. And nothing else is new. But since we are limited by computational power, and it is not a matter of increasing the clock frequency twice or double the number of processes, it's several orders of magnitude problem because we will not solve within the next 10 20 years. It is objective problem. One needs to simplify the problem in a dramatic sense. Simplify the problem, like reduce the number of degrees of freedom. Good. And I will go over the same information once again, maybe with some other slides, but we can interact and get basic ideas informally. So, which types of independent variables you did observe in the homework? Those are terms in Hamiltonian, but which arrows you start to draw? Positions. Positions of what?
Position of electrons and ions.
Yes. Yes. Exactly. Oh. We'll have what?
I'm sorry I'm late.
No, it's fine. It's fine. I'm very happy. So, there is nothing better than to see large attendance. So, if in the homework you had two positions for
Ion
Ion.
and
and one for electron, right? And if we count only distance between ions, then it will be one. One and one position for it. But each of them has three numbers. It's a function of 6 variables is possible. One wouldn't need to design new theory, but still it is not what we do in calculus and differential equations. What if we split problem on equation only for electrons and equation only for nucleus? So instead of 6 independent variables, we will have 3 and 3. This will be 3 independent variables is standard thing that we deal with, like electromagnetic field. We have fields of 3 independent variables. Any distributions in engineering or density, heat, everything is 3-dimensional. It's very standard. Sometimes we will have more than 3, but definitely splitting electronic and nuclear degrees of freedom in a legitimate, logical way would be really great. Okay, we accept this idea. There are too many degrees of freedom. We need to split electronic and nuclear degrees of freedom. Who ever took differential equations? Or good. And in differential equation in calculus, you may have seen the trick of separation of variables, right? So function of several variables is represented as product of functions of lesser independent variables. But this is possible only if differential equations includes each variable as a term, if they are not intermixed. And we need to check whether our molecular Hamiltonian has truly independent variables or they are intermixed. And you already know from your homework, from our earlier class, that there is a term of potential between attraction between electrons and nucleus, where in the denominator you do have both position of electrons and position of nucleus. This is a bad guy. This term forbids us to literally apply separation of variables.
So you mean that it's not possible to have an explicit solution for this equation?
Yes, it is not well. It is not possible to have analytic solution without any approximations. But one can design smart approximations so that the results will be very close to the real world.
So after that approximation, you want to solve this equation analytically or no, using numerical methods?
Nothing analytical, everything will be done numerically. So the equations are only for like art of approximations.
But with numerical methods?
Yes, yes. In some sense, what we are doing is related to applied math. So, not solving anything analytically, but setting up problems and setting up approximations that will hopefully lead to the correct answers.
What would be the method? What would be the method for that numerical?
We don't care because computers will solve for us. But in some sense, the major method of what we do is what computers does for us is diagonalization of matrices. So any problem is reformulated towards diagonalizing. Diagonalizing meaning finding eigenvalues and eigenvectors of matrices, and then they are interpreted towards our engineering and science problems. There is a little piece that you may know on your background thinking, but I'll better pronounce it before we go into details. There is a bridge between either analytical and numerical solution of Schroedinger equation for molecules of materials and observables, properties of materials in the real world. And this bridge is called expectation values. So after you have wave function, there is a protocol to find the observable, the expectation values on experiment. One can formulate them like intensity of light emitted by material, or electric dipole in this form in this material. Observables like this can be formulated based on the wave function. And finding observables is very well developed standard tool. So as soon as one has wave function, finding observable is a routine procedure that was developed for several decades. We will touch it in the course, but without wave function, there is no reason to look on observables. Yes.
So for approximation, you want to simplify the wave function. I don't know in which part we have biggest problem.
I enjoy our meetings very much. It's true intellectual analysis. So there is a term in Hamiltonian that will not obey, will not follow our wishes for separation of variables. But there is an objective property of all the systems. What is the ratio of the mass of electron and mass of proton? How similar or different they are? Who is heavier? Yes. How many times? Is it like 10 times heavier? 100 times heavier? Roughly. Huh?
And power. Not all.
Which other?
No?
No, less. It's about proton is about 2,000 times heavier than electron. 2,000, 1837, something like this. But 2,000 is good, and carbon is 12 mass of protons, so carbon is 24,000 times heavier than electron. So what does it mean, mass? It means inertia. So we need much more energy to to launch its motion. And heavier object move slower. Right? Light, if the energy is the same, then lighter objects move much quicker. And this is one of the key approximations. It rests on this fact. So both nucleus and electrons are charged. So if you move your nuclei, electrons will move in response because electric field is changing. But if we move by this and that reason positions of nucleus, so electronic positions will adjust instantaneously. So the pace of the change of electronic clouds in time is several orders of magnitude quicker than pace of motion of nucleus. And based on this fact, we will separate variables not literally as differential equations prescribe us, like in space of electrons, but we will, in some sense, one can say, we will separate them in time, because the motion and changes happen on very different time scales, and our main approximation today will be to split our Hamiltonian into two parts. One part, everything that is related to electrons that will move quickly, solve it, and then put the solution of the electronic part as additional term to nuclear part of it. So we will split and then reunite that. Okay, I think it is enough for introduction. Not enough. One, yes, please, and then I'll answer in a
What about the potential energy? Because if you assign different original points, the potential energy is different.
Yes.
So how to quantitate the potential energy, or how to determine the original point? Or it depends on different systems.
Thank you for asking. So we are departing, at least in our thoughts, from the psychology, from the philosophy of molecular dynamics when each particle has its coordinate. We will return back to it because it's really helpful, but for equations and for several lectures, we will depart to the world of quantum where everything is quantized. And if positions of electrons and nuclei are quantized, the question about initial position doesn't make sense. Because our wave function is distribution. It depends in space. So we assume that your electron and your ion can be placed anywhere in the space. And just depending on the position of ion, there will be a larger or smaller probability to find particle there. So it will describe all possible positions simultaneously. It's just philosophy of wave function. Make sense? So one more idea, and when we will go to the slides, it will be the last idea of the meeting. I know we discussed too many philosophical concepts, and they will fly out from the memory immediately if we don't open them again in slides. But you saw I was drawing like two clouds in the space. One cloud for electronic Hamiltonian and everything that changes quickly, finding solutions, and then putting it back into the part that corresponds to nucleus. So the very last idea. The electronic part, solution for electronic part, can solution of Schroedinger forms good basis set. And in the good basis set, we can represent any wave function, including the complete peak wave function of molecular Hamiltonian. Done. I'm tired. I don't know about you. This is why we put 11 a.m. Right? It was last year when no one was able to come morning. So we are separating electrons and ions. And last time we described molecular Hamiltonian, described that it's good to formulate something that will optimize geometries and find electronic properties, and we discussed that in the Hamiltonian that always consists of kinetic and potential terms. And we also covered that the time-independent Schrödinger equation is more narrow and more generally time-dependent Schrödinger equation, where Hamiltonian is operator of total energy.
Yes, can you speak a little more about the top equation? I don't understand it. What is the difference between, you said one of them is independent, one is dependent.
Time independent. Time dependent because there is derivative for time, and this one is time independent because there is no time. And Hamiltonian itself includes derivative over position. But in this equation, there is no derivative over time. And if you are so curious, then so if one assumes one force so if one assumes that if one assumes that wave function that enters the time-dependent wave function has the form of time-independent part, wave function that doesn't depend on time, times oscillating factor. Right? And this is complex, imaginary unit. You're fine with complex, right? Then plugging in this equation into here will give you this equation.
What's the meaning of H bar again?
H bar
Is it constant?
is a Planck constant. Planck, not like H bar, not the one that one makes pull-ups. It's bar because there is a line, and Planck is the name of the scientist. So the dimension in SI units, it's very small number. It's like 6 times 10 minus 34 joules times seconds. So it is very small number, and it enters every. You can write down Planck constant. You'll find it in Wikipedia.
the dimensions of Planck constant are either energy times time or position times momentum. And the meaning of the Planck constant, it was like a very fundamental cornerstone of quantum theory. The original Bohr theory for hydrogen atom used a hypothesis that angular momentum, which is position times momentum, can take only discrete values which are equal to integer fractions of Planck constant. So if angular momentum, the rotation of electron around nuclei, can have the values of angular momentum equals 1 h bar, 2 h bar, 3 h bar. And based on this hypothesis, we can reproduce the spectrum of hydrogen atom. And in the equations, it sets up the scale of dimensionality. If energy times time, or if angular momentum is substantially bigger than Planck constant, then one can neglect quantum properties and do standard Newton's equation of molecular dynamics. If we are dealing with sizes, times, and values of angular momentum, it brings us to the limit of Planck constant, one has to do Schrödinger equation. Enough? Okay. Oh, yes. So this is not always and not absolute truth. It is for Bohr's model, where it is originally used. So z projection of angular momentum, which is equal to product of momentum times position for electron that revolves around the nuclei. Here is I, here is P, so the values of this product R times P, or value of angular momentum, which quantifies the speed of rotation, takes only discrete values equals to Planck constant. Good. And this is summary of quantum theory, which we will not need more if it would be easier if we would have unlimited computational power. We need this arrows, and the molecular Hamiltonian includes 4 terms: kinetic energy of nucleus, kinetic energy of electrons, repulsion of nucleus, repulsion of electrons, and electron to nuclear attraction. Good. So this is molecular Hamiltonian, and about now, yes, about now we actually started the lecture. After review and introduction and review. So you have noticed that if we will try to describe really realistic materials with hundreds of atoms and thousands of electrons, the list of arguments in the wave function will be very long. You will need to write R1, R2, R3, and I don't know about you, I'm lazy. I cannot write 100 numbers without reason. So there is a convention. If we have a set of numbers like R1, R2, T, and then R number of electrons. We can just tell that it is R sub I in brackets, just to pay tribute to laziness. And the same if you have positions of R first of nucleus, R set R number of nucleus. You can tell that it is the same as round brackets. And in these new notations, we can tell that our molecular chemistry acts on a wave function that depends on a set of positions of nucleus, set of positions of electrons, and as a and if it is wave function is selected correctly, we will get the same wave function and the eigenenergy of the ground state of the system. So this time differential wave function. And there are some silly questions put in here, which are evident answer. It's definitely an ugly equation because it has too many independent variables. It's definitely very hard to solve. And most difficult is the number of independent variables. Right? Are lowercase. And the third, I was giving some examples. We don't need to go over them, but if one assumes that we have like H2 molecular hydrogen or benzene molecule with 6 carbons and 6 hydrogens, which looks like very simple for chemistry. It will be 12 nucleus times 3, 36 independent variables in positions of ions, and then each carbon has 6 electrons, 36 vectors, and each hydrogen has 1 electron, 42 electrons. 42 times 3, 126. So 126 plus 42 will be like 148 independent variables, even for small benzene. It's ugly, it's not possible to solve. And there is no reason to solve. One can get any properties of the benzene molecules which much simpler numerical effort if we follow the ideas and then do some calculations. So we need equations. I agree. And we already discussed that separation of variables is possible when differential equation has terms including only summation of these independent variables. When there are no products, there are no cross terms. And then separation of variables would work. So here is an example. If you have a function of 2 variables, separation of variables means to simplify it to one-dimensional function 1 and one-dimensional function 2. It depends on the first and second variable. But this trick is possible only for a limited number of differential equations when there are no cross terms. So we want to do the same trick with nuclear and electronic degrees of freedom. Because it would be wishful to have our overall molecular function as a product of wave function that depends on the positions of ions, and we will try to use the letter theta, and wave function that depends on the position of electrons. If we can do it, it would be really great. But we already discussed that it is not quite possible without some approximations. So in molecular chemistry, we do have this nuclear to electron attraction, which depends on positions of both nucleus and electrons. It's a cross term that makes our life a little more complicated. But there is a trick, and there are people who design this trick. I recently visited a research lab at Los Alamos, New Mexico, and there is a street, like Oppenheimer Street in the city center, because he was working there. And these two guys were developing this trick because it was objectively necessary even before computers were coming. Maybe it was more necessary because human power is less than computer power. One needs to simplify everything. So the idea about different inertia, different mass of electrons, nucleus, and correspondingly separation of Hamiltonian into parts, then filling them back is credit to Born and Oppenheimer, and therefore the thing that you cover today will start today and complete on Thursday is called Born-Oppenheimer approximation. So it's a careful, legitimate way to separate our point of nuclear degrees of freedom. Just a little entertainment that you can skip this because we need to take a breath and relax before we go to intense thinking. So when we will complete about 75% of the course, you will select which projects you want to focus on. And likely you will select something you're already doing in your major research groups. But if you need additional ideas, they will offer several options. Those are options from the first time this course was offered. Now I will offer something more interesting. It's just general ideas what can be done by population. So which materials, and some of them were for people involved in science and chemistry, and therefore they were a little smaller and simplified. But like molecules on surface of metal is, or on surface maybe graphene, is something that could be of interest. So this is all doped crystals for lasers, or maybe chemical reaction for Star Wars, or for chemical lasers. Okay, after a little relaxation, I invite you to focus. And you've noticed there is a slide that is labeled as every most important. So, if we consider the inertia of electrons and nucleus, it's like a mouse and an elephant, or maybe an insect, a fly and an elephant. So for a fly, the elephant is not moving. So we can assume, if we are interested in electronic degrees of freedom, we can consider that positions of nuclei are frozen. They are moving so slowly that we do not observe them. So, and they will be like parameters. So this is main philosophical idea behind the next steps. So the plan is to develop equation for only electronic degrees of freedom. Assume that we can find their solution, because right now at the beginning of the course we lay philosophical foundations. Later on, we will carefully solve. But now we skip solution for future and assume that we can solve electronic part and insert this solution back into molecular Schrodinger equation as a basis, assuming that it is a good basis. It's quite boring, quite philosophical, but importance of these steps is that language in the community of people who model materials, these computation tools, is based on this approximation. And one way is just to memorize, like to cast a spell. Everything I do is based on Born-Oppenheimer approximation. And then, if you do not know what it is, you can do it and write it in the paper. But if you answer to reviewer, and some of you are already exposed to it, some of you will definitely will be. So if you need to make a publication, it's a peer-reviewed procedure. So reviewers are trained by authors, and they are asking details about approximations or about methods. And if you get some understanding of the background, you will be more efficient in addressing this potential questions. Or if you make oral presentation in front of public, you need to be armed to answer these questions. So what we are covering now is irrelevant to practical work. It's more like foundations and preparations to participate in the discussion. Okay, that is most important. A little trick. Remember how we were ordering terms of Hamiltonian before? It was T, T, V, V, V. Right? Now I offer you T, V, T, V, V. So we put T, N, V, and N. So everything is related to nucleus first. And then everything that has E there. T, E, V, E, E, V, and E. So these two terms definitely relate to electrons only. And this bad guy was like doubtful where to put it or treat it separately. Because of inertia, of big inertia of nucleus, low inertia of electrons, because flies consider elephant as very static, we attribute this part of Hamiltonian to this group. And then true electronic, and this is something not quite electronic, but it is very related. The selection of word is not ideal. Probably with years I can find something better. But we are going to pull these three terms of Hamiltonian, of molecular Hamiltonian, and consider it as partial Hamiltonian that will act on the partial wave function that we need to find. And a lot of calculations is done this way. So one completely neglects anything related to nucleus, considers them as nailed down, fixed, and just solves only the electronic part. So this problem is interesting and useful on its own. But if you take only this part of Hamiltonian and find its eigenvalues, you can use it backwards to solve for the complete molecular Schrodinger equation.
So it's going to be particular solution.
Mm-hmm. And when we focus on this circular part, the positions of nucleus are parameters. We can change them, but they are not independent variables. We are not solving as functional. They are like constant that can be tweaked. for electrons positions, ions parameters. So what? It's not optimal choice of the word, but this under this fake electron, I assume kinetic energy of electrons, repulsion energy between electrons, and attraction between electrons and static nucleus. If we would do in mathematically ideal separation of variables, this part should depend only on positions and momenta of electrons. And those are two independent variables. But dependent variables. But since true molecules, true materials can be realized with slightly changed positions of nucleus, like if I can squeeze it or accelerate by light and they will be on a slightly different distance, we still need to have the positions of ions, but they will be like parameters. They will not be independent variables, but they will be explicitly included into the equation. So there is a missed symbol. Maybe right here, right there. So it is an equation, eigen vector and eigenvalue equation. So by solving this equation, one finds this phi of the set. Okay, set of the wave functions that are labeled by index A instead of energies. And the energies will be different if we slightly move the ions, if we reset the parameter of positions of ions. Therefore, energy is not constant labeled by index, but it depends on the positions of ions. Now we have the natural question, whether solving this equation and finding these wave functions and these energies will help us to find solution of the overall molecular Hamiltonian and molecular Schrödinger equation that we set up. I'm going to appeal to your background education and check some concepts if you're familiar with them. One concept is from basic calculus, is Taylor expansion. Give me a little sign if you're aware of it, right? Taylor expansion is when you take arbitrary function in the vicinity of some point and then represent function as a series of the value of function at this point plus derivative times x plus second derivative over 2 times x squared, right? Polynomial expansion. So you represent a function in a certain limits as the summation of polynomial functions, of power functions. So good. Another concept, Fourier series. Okay, so in electrical signal processing, one represents superposition of several oscillating signals and by adding them together, one can get any shape of the signal. In this sense, in previous example, polynomials were basis functions. In Fourier series, the sine, oscillating sine and cosine functions set a basis. So by adding together basis functions with correct coefficients, one can represent any function. So any well-defined mathematical function can be represented as a summation of correct basis functions with correct coefficients. I'm so happy. I was staying ready to cover it from scratch, but if not needed, it's good. So, connection. How does this solution of this equation contribute to solution of overall molecular Schrödinger equation? Solutions of this electronic part will be considered as good basis functions. And by adding them together with appropriate coefficients, we will build solution of molecular Schrödinger equation. Okay, I think it is a little assignment to myself. I'm not going to invite anyone to write it. I'll do it myself. So this is the nuclear part, this is the electronic part. This should act on the big function that depends on both electronic nuclear. It will be total energy times this function that depends on electronic. And we are going to implement the idea about basis functions. So this is solution of molecular Schrödinger equation. So we will use solutions of the electronic part of the stuff that diagonalizing of what I wrote with or not efficiently called fake Hamiltonian. Electronic part which includes interaction with electrons. We will use the solutions with indices A as basis functions. We will add them together, and we will believe that if coefficients here are taken correctly, we can get solution for overall molecular Hamiltonian. And coefficients here will be functions of nuclear positions. Question?
So, for this to solve this function, we are assuming that nuclei are constant. They are not moving.
For finding this function, for solving the equation on the previous slide, we assume that positions of nuclears are constant. But now we are using these functions. We are just taking them as a package from the web box and use them as basis functions to find overall wave function of molecular Hamiltonian, where electrons and nuclei can take any values. And then the expansion coefficients for this trick. Expansion coefficients. At the same time, this expansion coefficients are playing a role of nuclear wave functions. Like if it is hydrogen atom, interatomic distance, hydrogen molecule, then this wave function will have the maximum when they are on the correct interlink distance. It will have a little Gaussian. Okay? So this is basically the last idea of today's meeting. We are going to use the language introduced in these considerations in whatever we do next. On Thursday, I know it is not quite fair because we didn't start actual calculations and we have mathematically intense things. So please prepare, drink coffee before meeting. On Thursday, there will be most complicated lecture in amount of equations and their level of complexity. When we will continue the course, everything will be easier because foundations are hard. And I will try my best to simplify it as much as possible.
And can you please address some part of the book that we can review for these materials that we covered today? For instance, yes, there is some references and
yes,
to be more.
Yes, I feel not super comfortable in like disclosing copyrighted things, but probably for educational purposes I can copy one page.
Or address some pages or just.
But I can suggest what to look at.
The suggestion would be enough. We can find the relevant parts.
Okay. There is material. Probably I will bring some printout on the next lecture so that that will duplicate what I'm telling on the different language. Okay. I mean, in a different, not like in Japanese, okay, but by different words.
Okay. Thank you.
Yeah, thank you for the interest, and it's good to have a second option. Yeah, the same equation, just typed in maybe a little better than my bad calligraphy. So previous functions, expansion. Oh, it's the theta use chi. Now it doesn't matter, but we just need to select.
It doesn't matter.
Now it doesn't matter, but at least during the next lecture I should select and give the same notation. Okay. Position minus. So during the next lecture we will do some mathematical steps that will lead to definition of potential energy surfaces, which everyone who does molecular dynamics is already well aware of. But there is a rigorous definition, not just from intuition, but from the point of view of all these mathematical processes. There is a concept called non-adiabatic coupling. Typically it is removed from all calculations, but one needs to be aware of it. And yes, and concept of matrix elements. You were asking question, interesting question, like which mathematical equations are being solved in the computational chemistry tools? And the answer was finding eigenvalues and eigenvectors of matrices. So the Hamiltonian in certain ways can be formulated instead of differential operators in form of a matrix. And then if this matrix is diagonalized, one can roll over into everything we need. In previous years, I think it was a question after the lecture, and I was given a little example. I don't know if you need it. It's oversimplified. Typically, we'll diagonalize matrices. Computer will diagonalize matrices like 10,000 by 10,000 for us. So the Hamiltonian is typically a differential operator. But if one represents this differential operator in a basis of certain wave functions, one can convert the Hamiltonian into a form of a matrix. In the simplest possible case, it's 2 by 2 matrix. Then, in a basis, a wave function looks like unknown coefficients, vectors. And eigenvalue problem.
Your call will be disconnected.
The vector gives the same vector with energy. Enough. we should ask director of tech support to have this meetings on the record and connection for a little longer. So, but right now it's a signal that we need to finish.
Oh, one question. I didn't catch this part. Oh, could you go back a little bit?
Yes.
Go back, back. Go back. Oh, yes. So for the electron Hamiltonians, you have true electronics and fake. So why you just consider the fake electron?
I've got the question. This part relates only to nucleus. This part relates only to electrons, and this relates to both electrons and nucleus.
Yes.
So there is no. If we will not have the ideas of Born and Oppenheimer, if you would try to solve it mathematically on our own from scratch, there is no prescription to attribute this one to electrons or to nucleus, because it depends on both of them. Just because of scientific intuition, because of the idea that electrons move quicker than nucleus, it is more efficient to attribute this part to electrons. But it is not rigorous prescription from math. It's our scientific intuition. Therefore, fake is not a good word. I would use something like intuitive assignment. So this interaction between electrons and nucleus is more optimal to be attributed together with other electronic terms to form the Hamiltonian that will describe electronic properties, assuming that nuclei are floating. Other thing, if we assume that nuclei are not moving completely, then these terms, instead of operators, will become constants, and our Hamiltonian will consist of this one. So it.
So you mean we can ignore the true electronic?
No. We can ignore if it is absolute zero. If our nuclei are absolutely heavy,
yes,
if they're not moving, we can ignore this thing. But we cannot ignore this one because it includes electron position that can change even at zero temperature.
Yes.
So these three terms cannot be. Should be together based on scientific intuition and analyzing of properties of materials.
But the momentum of electrons is larger than the nuclei.
Yes.
So for the
this is
yes.
momentum of electron comes here,
yes.
and we do not neglect. We keep it. So we take only we take the blue circle as standalone, as independent Hamiltonian, and try to find its eigenvalues and eigenvectors. Make sense? You let me go? or more questions? I'm happy.
Thank you.
More questions 1, more questions 2, more questions 3 solved.
So we should submit the assignment today?
Oh yeah, I'll collect.
Thank you.
And looking forward to see you Wednesday, 5 p.m.
Okay, and you were supposed to tell us about the final hours of the class.
11.
The next Thursday?
Yeah.
Yes, Tuesday, Thursday, 11, Wednesday, 5.
Okay.
I've sent an email this morning.
Oh, I didn't.
There was, for Thursday, it was for sure, majority, almost everyone is able at 11. And for Tuesday, it was like 5 out of 7 for 10, for 11, for 12, for 1. So it was equal amount of votes for several hours. But for me, 11 is better. So I just added my votes. Thank you. Oh yeah, absolutely. Thank you.